will, I promise, to consider radicals, but actually one small theorem which I will also formulate and prove. And I'm interested in the proof mostly because it shows how to deal with the differences between the real and complex cases. You know, the problem is that a complex matrix, excuse me, a real matrix can have complex eigenvalues. And by this reason, it is even not always true that an operator in the real vector space has any eigenvector at all. By this reason, for example, the Lie theorem, if you remember what it is proved over the complex number, if you wish, if you wish this algebraic language, the algebraically closed field. But still, sometimes theorems can be, not the Lie theorem, but some other theorems can be somehow translated from the complex case to the real case. And this is one of them. So, theorem. It's very simple. Suppose that we have some representation of some Lie algebra. And at the moment, I do not say that this Lie algebra is real or complex. But I assume that this is solvable. Then I consider the ideal, and this is an ideal, certainly, n if G in G, which consists of those Xi, what's my notation? Yes, Xi in G, for which rho of Xi is nilpotent. Rho of Xi is an operator in V. Then I claim that eta is an ideal, and moreover, actually not moreover, but I say moreover, it contains the commutator subalgebra of G. Look at this. Well, first maybe I should start with this. Certainly the second implies the first immediately, because if it is true, then n is n is between G and G prime, and hence it's an ideal, because the commutator of n and G is a subset of the commutator of G and G, which is G prime. So this is obvious. So this direction. So I prove this. Well, consider any Xi, set that rho of Xi, is nilpotent. Actually, according to the Lie theorem, any rho of Xi for any Xi in G in an appropriate basis in the complex case, which I now consider, is presented by a matrix like this, right? Now, the question with the obvious answer: how is it possible that this matrix is nilpotent? This matrix is nilpotent if and only if all the lambdas are zeros. Right? Obvious, right? Obvious. If and only if. So if rho, and the other thing, this set is precisely means that Xi belongs to the commutator subalgebra. You know, the commutator of any two matrices of this kind certainly has zero magic. So what we have, well, what direction? This direction. So what we have, that yes, if this operator is nilpotent, then actually it belongs to, no, if, if C belongs to the commutator, then it belongs to N. So N contains the commutator subalgebra, which resolves all the problems in the complex case. Okay? Now, how to deduce the real statement from this? And for this, there exists such a spell which resolves all these problems in many cases. I will use it from time to time, but now let us pay some attention to it. The word which makes the whole thing done is what? Just one rather long word: complexification. And in this case, it works perfectly well. So if G is a real Lie algebra, and V is real, and everything is real, then we can complexify everything. So this is what? G sub C. If you prefer that they use algebraic notations, this is G tensor C. This is a complex Lie algebra. With the same basis, if G has some real basis, and this has the same base over the complex numbers. V is the same. We can complexify everything. And the last thing which I need to say, that this complexification operation respects the commutator subalgebras. What is commutator subalgebra? It is something spanned by commutators. If you wish, commutators of the elements of a basis. And as soon as we have this, basis is the same, everything is the same, only the word span now has a different sense because we span over complex numbers. Actually, statements like this, if we prove it for the complex case, for this, it's immediately true for the real case. This will happen quite often, and sometimes I will just say that complexification, and it's okay. We use some purely complex facts. Roughly speaking, we use that a linear operator has an eigenvector. Prove some theorem, but if the theorem does not involve these eigenvectors, but something about the spaces, then usually the complexification immediately resolves all the difficulties. Have questions about this? Still, my statement is this. But by the way, in particular, this implies that, in particular, if you apply it to the algebraic representation, this implies that the commutator. Yes, if you don't leave. So the following statement, that a Lie algebra is solvable, and you will say to me whether it is clear immediately. A Lie algebra is solvable, the algebra G is solvable, if and only if G prime is nilpotent. Solvable, G is solvable, if and only if G prime is nilpotent. Why? In one direction, it is too obvious to speak about this. If G prime is nilpotent, then solve is solvable. Nilpotent algebras are solvable. Now this sequence, G, G prime, G double prime, G triple prime, and so on. The solvability means it's finite. But if it's finite for G prime, it is also finite for G. Right? So this is immediately true. In the other direction, that is, if G is solvable, then G prime is nilpotent, it follows from this reference, rather this reference to the Lie theorem than anything else. Now I promised last time that we'll discuss radicals. we have an arbitrary algebra, there are two notions which are called radicals. Radicals, which is important, and nilpotent radicals, which are also sort of important. First of all, we actually consider not Lie algebra, we consider representation. G is absolutely arbitrary algebra. I, again, do not care about the field. If you are too strongly on the algebraic side, I can say that better to assume that it is not it is of zero characteristic. If you are reluctant to do this, characteristic 2 is destructive for the theory. Well, but for us, real complex numbers, I do not go this far in the algebra. Now, so we have this. Now, suppose we have an ideal, and just I want to follow my notations. Yes, suppose that I have an ideal, n, in G, say that the restriction of rho unto n is nilpotent. You understand? So nilpotent representation is a very simple thing. All the operators are nilpotent. There may be many such ideals, for example, 0. Now I denote by some strange letter the set of such ideals. My claim is that actually this set has a unique maximal element. That is, there exists in N a very special ideal, which I denote as N sub rho, so that it contains every other element in N. So say that N belongs to N, even on leaf, N is contained in N rho. This is the theorem. Please somehow approve this statement. And now the proof. It is not immediately obvious, at least the proof which is done in my notes is not just one word proof. Because I need to consider two cases. The transition from the first case to the general case will be very easy, but still. So, case 1. Rho irreducible. What is irreducible? This means that the space V does not contain any proper invariant subspaces, no subrepresentations, except 0 and itself. You understand? So I suppose that rho is reducible. Then I want to say that n, well, that the n rho should be taken for this. Just kernel rho. Rho is a map of G into GLV. It can have kernel, so the elements of G which give rise to 0 transformation, and it is an ideal. And actually, I want to say that an ideal satisfies this condition if it's on leaf. If it is so, a representation, an irreducible representation of G on well, so let me say this now. You see, there is the theorem by Engel. We said that any representation of whatever you have of n, of n, of any important algebra, has a certain structure. So there, if n belongs to n, and this actually is even on leaf. If n belongs to n, then there exists, in particular, a non-zero subspace in V, so that it is annihilated totally by all elements in row of n, right? Certainly it is a sub-representation. Yeah, it is clear that it is very much invariant with respect to, if n is an ideal, it's very much invariant with respect to the action. Action of G actually. If V is irreducible, then a sub-representation which is not zero should coincide with the same, with all. So what we have, we have that every element of n should belong to kernel of rho. Any element of n, whole n, if V is irreducible, should give you zero representation or any important transformation. Well, you understand what I say. So the fact is that if rho is irreducible, then kernel of rho is obviously the thing which we are looking for. What to do if rho is not irreducible? Again, in this case, we don't need to do much. There is some obvious thing. I will say this, and you will agree or disagree that it is obvious. So V is an arbitrary representation. But I want to say that there exists a chain of sub-representations. Sub-representations such that every quotient is irreducible. Well, certainly it is so. First of all, we can find a minimum irreducible sub-representation. Take just sub-representation. If it is reducible, then there is one. If it is reducible, it's okay. If it is not reducible, take a sub-representation of it and do it until you get an irreducible representation. It will be V0. Then factorize over V0 and do the same. In V factorized over V0, you find an irreducible representation. Then you lift it. It will be in V factorized over V0, you lift it into V, and it will be V1. And the quotient of V1 over V0 will be reducible by this construction, and so on. So this is sort of obvious. Now, all these spaces, which is also obvious. No, I just said this. So all the spaces are sub-representations. So rho can be actually, there is rho I here, which is irreducible. So this is induced by rho. I take rho, I restrict it to Vi, and I factorize over Vi minus 1. From this it follows that n is in my n, certainly is contained, in kernel of every rho I. Because this is a representation, so my previous construction says this. And hence n is contained in the intersection of all these kernels. And that's all. This intersection, obviously, this is an element of capital N, and this contains every element in N, so this is the maximal element. So we have this thing, this very special ideal N rho. It will be important for us to apply this construction, this result, to the case of the adjoint representation. So, if rho is a representation, then everything remains, and n add is called the nilpotent radical of G. So in G, there exists this ideal n add nilpotent, which contains any other nilpotent ideal of G. This is what we have. It's called nilpotent. This is very much unique. It contains it. It's called the nilpotent radical. One thing probably should be said. Something which could be wrong, actually right, is actually wrong. It is not right that n rho is just the collection of all elements of G for which the operator rho of all C in G for which the operator rho of C is nilpotent. No. This is not an ideal. I'm even not sure this is subspace. So this is an ideal, a maximal nilpotent ideal. This, well, so far nothing else. So far nothing else. Now radical is a more, how to say, more popular object. Again, we have a Lie algebra, G. Now we consider the set of solvable ideals. Nilpotent and non-nilpotent, all solvable ideals. And there is such a very simple circumstance that if we have two solvable ideals, H1 and H2, then if their sum is also a solvable ideal. It is checked absolutely directly from the definitions of an ideal and solvability, but to make things less clear, I can say how it is normally proved in the textbooks. So H1 plus H2. It contains H1. No, you will not have objections. Now the quotient is the intersection. Again, probably you will know the quotient is not the intersection, is the quotient of H2 of the intersection. This is better. And now there are simple properties of solvable algebras, which I'm not sure that were ever pronounced here, but it's so obvious. So H1 is solvable, H2 is solvable. This is also solvable, the intersection certainly. Any subalgebra of a solvable algebra is solvable. You understand this? For solvable algebra, you take H, you take G, G prime, G double prime. If H is contained in G, then H prime is contained in G prime. So as soon as you reduce algebra G to a smaller algebra, all the sequence of derivatives will be also reduced. If the first ends by 0, the second will also end by 0. So this is solvable, this is solvable. This is solvable. And we have that this thing, this ideal is an ideal, it is obvious, contains a solvable ideal, and the quotient is also solvable. This is sufficient to say that it's solvable itself. Again, very direct verification. So this is sort of an obvious thing. So we can take sums of solvable ideals, and that will be solvable ideals. This certainly gives me an immediate reconstruction of the biggest possible solvable ideal. Just take the sum of all of them. Yes. So you can inflate and inflate it. You have a solvable ideal. If you have a solvable which is not contained in it, take the sum of them. If this contains any solvable ideal, then stop. If there is a solvable ideal which is not contained in the sum of the first two, add it, and so on. So in this way, certainly in the finite dimensional case, you can find the maximal solvable ideal. And this maximal solvable ideal is called the radical of the Lie algebra. So the radical of Lie algebra, real or complex, by definition, is a solvable ideal, the unique solvable ideal, which contains all other solvable ideals. So we have the following things. The notation should be established. Nilpotent radical of G and radical of G. How are they related? Certainly this is contained in this, because this ideal, this is a solvable ideal, and this contains this because this is nilpotent. So nilpotent radical is something between the radical and the derived functor, the Howden function, the derived algebra, the commutator subalgebra of radical. Nilpotent is somewhere between these two. It may be equal to any of them. Good. Yes.
So this sums of nilpotent ideals need not be nilpotent, or
Sum of two nilpotent ideals? No, it should not be nilpotent. This is an interesting question.
I think it should be.
Should be.
You've reached enough power so that all the terms are to the same power. At least
Especially if they commute.
well, even if they don't, right? Well, okay. No, you're right.
No, I don't think so. Well, question remains open. I don't think so. I think it's very easy just for matrices.
I'll look into it.
Yes. Take two matrices with zero eigenvalues. Two Verso matrices. Then there are some I don't think that the eigenvalues will be all zeros. Yes. Immediate example. You take this matrix and this matrix. I will not give a half penny for the statement that the sum is nilpotent. But each of them is nilpotent. Well, now the main word in this course. So this is the moment. Lie algebra is called semi-simple if its radical is zero. If it does not have, non-zero solvable ideals. Very strange definition. Why semi? Why simple? Why? I can say something immediately. There are some immediate facts which I will not even check because they are not too interesting to check. Certainly, if you have a nilpotent, semi-simple, some Lie algebra, and it has a semi-simple subalgebra, and the quotient, semi-simple ideal, and the quotient also happens to be semi-simple, then the whole algebra is also semi-simple. It is very easy. You just look at solvable radicals and see it immediately. So this is true, that that such extensions, so we have two semi-simple Lie algebras, and then Lie algebra which has one as an ideal and another one as the quotient of this ideal, also semi-simple. For example, if we take a direct sum of two semi-simple Lie algebras, it should be semi-simple. This certainly statement which can be called only deplorably weak. Because actually, look, there is such a thing as simple Lie algebra. Simple Lie algebra is something very pure. It doesn't have ideals at all, solvable or not solvable. So it should be semi-simple. So the sum of two, well, with only one exception, one notable exception. There is a solvable Lie algebra, which is also simple. It's one-dimensional algebra. The one-dimensional algebra, which is very much commutative, however, it doesn't have simply not space enough to, not room enough to have ideals, so it is simple. And it is not semi-simple because it's solvable itself. So this is a good example of a simple but not semi-simple Lie algebra. No other examples. The fact is that it is a two-sided statement. A Lie algebra is semi-simple if and only if it is a direct sum of simple, not commutative, not one-dimensional, which is the same, Lie algebras. This will be proved eventually. It is not too hard, but no, it's sort of hard. Yes, because no, the proof will be one word, but it will use a lot of things. Yes, but this is true. This we will see this eventually. And now I mentioned for only one reason, that it justifies, in some sense, the term semi-simple. Semi-simple is, roughly speaking, the sum of simple Lie algebras, with the exception of commutative algebras. If we do not make this exception, then the resulting notion also has a name which I'm not sure that I will be used here a lot. Reductive Lie algebra. Reductive is simply the sum of simple Lie algebras, commutative or not. But what we consider here is the notion of semi-simple Lie algebra, which is the sum of, will be proved eventually, sum of simple non-commutative Lie algebras. That's all. Now the thing, the first thing, which is actually the main instrument in, maybe I should say this, I don't know whether it is sufficiently clear now. The semi-simple algebras will be very important to us. This actually is, in some sense, the main object of our study, and although so far we consider nilpotent algebras, solvable algebras, they will be also important, but mostly as subalgebras of semi-simple algebras. Semi-simple algebras is the main object of our study, and main instrument is the so-called Killing form. So Killing, Wilhelm Killing, German mathematician, it is maybe not precisely fair to say that he invented Killing forms, although he used them in his works. Killing, there are such mathematicians even in our time, which actually understand a lot, but do not have any inclination to provide rigorous proofs. Well, somehow. Many people dislike them. And there is a reason. Because, you do something, somebody says, the theorem belongs to me, it was published by me 20 years ago. But where is the proof? Well, I understand that proof maybe was not complete, but I had it, simply I didn't write it, and so on. And certainly it creates some misunderstanding. So it is better, actually, when you have some results, better publish them with reliable proofs. Otherwise, it sort of may create. The community, from my point of view, actually usually do not accept such statement that somebody was to somebody because, well, it was mentioned in his work without proof, without understanding, without. If you apply this criterion to Killing, it will kill him. Because actually he made different statements. For example, the beautiful classification theorem for finite dimensional complex semi-simple Lie algebras, simple Lie algebras. It actually belongs to Cartan, to Lie Cartan. We will do it here. But It also was stated by Killing. And Cartan, in his work, said that he gives a proof to the following theorem belonging to Killing and so on. Cartan, in this respect, was very generous. Many other things, Killing form also. It is something which is called Killing form, and we should have some respect to Killing because his understanding was very deep. But still, precise definitions, precise theorems, and so on usually don't belong to him. So, Killing form is the following thing. We have a representation of a Lie algebra. Real or complex, whatever. Then I define the number for two elements, C and eta in G. I write B super rho C eta is equal to the trace of the composition of these two operators. In some sense, the idea here is quite deep, because when we have a representation of Lie algebras, then these compositions actually don't belong to this representation. It is not an element which corresponds to any element of the Lie algebra, because only commutators belong. If you have a row of the commutator of C and eta, then yes, it is a row of some element of the Lie algebra. This is something sort of external for the Lie algebra and the proper algebra which is related to the Lie algebra. Maybe we will consider it here, not very extensively. It's sort of based on this idea that actually if you have a representation of Lie algebra, you have many operators which do not belong to the representation. This is one of them. Well, this all may mean nothing to you. What means something? First of all, this B, it is a real valued or complex valued form, very much bilinear, but also symmetric. So this is certainly equal to B rho of eta C. Sometimes we are in some unknown territory, because in the complex case, it is more common from the point of linear algebra to consider Hermitian forms. They will provide a compact group U of n. Many things are related to and this symmetric. It is not known by. Now, let us consider some the Killing form. First, the following invariance property. For 3 for any 3 elements of my Lie algebra, this equality holds. This is sort of obvious. I can just show my respect to this statement. It's the most basic statement, invariance of the Killing form. Invariance means this. Always means this. So I can just write on the board some proof of it. I write B rho of rho of xi z zeta rho of eta, no, trace of this, which is the left-hand side of my equality, is the trace of this. So this is what? rho of xi, rho of zeta, rho of eta, right? Minus minus rho of zeta, rho of xi, rho of, right? Now, what I do now, I just take the second. Maybe I will not even write anything else. I will take the second part, this part, and trace, you know, has this property. The trace of a product is equal to the trace of the same product in the other order. So I can take this and swap it. Then rho of xi will be in the first position in both cases, and certainly this is equal to this. If you don't see this, I can write if xi is now will be xi, then eta, then zeta. So xi is in the first position in both expressions, and the second rho of zeta, rho of eta minus rho of eta, rho of zeta. So yes, it is this. Will I be able to say both? I will try. Let me begin with the second thing. Maybe it is more immediately important. Certainly, we can take for my representation rho, can take the adjoint representation. Then we have a form B rho, B ad, which is usually denoted simply as B, or BG, the Killing form of the Lie algebra itself. It is the Killing form, it's adjoint representation. Certainly, it is a Killing form, so it has the invariance property as before. But actually, it has a stronger invariance property. Namely, imagine that you have some derivation of G. It might be inner derivation, maybe not inner derivation, some derivation of G. Then we have the following statement: Bg of dxi eta is equal to minus bg xi d eta. If d is commuting with some zeta, then it is precisely the previous thing. Well, this is the proof is several words, but let me, maybe I skip it now. Actually, the proof is one line. You can do it yourself. It is not a problem. I just want to make some statements that you understand where actually everything comes from. From the invariance, it is a very actually simple statement. Suppose that we have some representation rho of the algebra and have some ideal. So rho is representation, arbitrary, and H is an ideal. Well, a bilinear form is a bilinear form. It provides some orthogonality. You understand that there are orthogonal complements to subspaces. If the form is not degenerate, which it didn't say, then the dimension of the orthogonal complement is equal to the codimension of the space. You understand? The sum of dimensions of a space of orthogonal complement is equal to the dimension of the whole space. It's true. If, however, the form is degenerate, then actually, even in the non-degenerate case, these two spaces, a space and orthogonal complement, very much may have non-zero intersection and, even strange to pronounce it, they may coincide. And those of you who are familiar with symplectic geometry know that there are special subspaces of a symplectic space which are orthogonal components of themselves, and they called Lagrangian subspaces. Well, I didn't say this. So dimensions, yes, okay. In the general case, when we don't know that the form is non-degenerate, it may happen that the orthogonal complement is bigger than that. The sum of dimensions of the space in the orthogonal complement is greater than the dimension of space. Still, there are orthogonal complements, and my statement is that the orthogonal complement with respect to H, with respect to this form B rho, is also an ideal. This will be important. And now I want, there are some other, let me two the most important things. The thing which people usually know, and I am glad to say this to you. Lie algebra is semi-simple if and only if its scaling form is non-degenerate. This may be called the Cartan criterion for the semi-simplicity. But actually, there is another Cartan criterion. I will formulate even, I have no board, but I will say this. The algebra G solvable, not semi-simple. If and only if the algebra G prime, that is the commutator subalgebra, is contained in the kernel of this form G. What's the kernel of a form? A kernel of a form is degenerate, is the set of vector Xi such that B, C, eta is 0 for any eta. The algebra is solvable if and only if its commutator subalgebra is contained in the kernel of the representation. I can say if the algebra is not solvable. Form is 0, then the algebra is nilpotent. It's somewhere between nilpotent and solvable. The Cartan criterion for the solvable the algebras is the only thing in the theory which actually requires a proof. All the rest follows immediately. No work. In turn, the Cartan criterion for solvable groups depends on a very elementary lemma from linear algebra. Those of you who teach linear algebra, I don't know how many of you teach linear algebra, can use it for a quiz. But it is sort of not quite obvious. There is some statement from elementary linear algebra which actually has a proof, half page, maybe 3/4. Then from this, more or less immediately follows Cartan criterion for solvable algebras. From this, more or less immediately follows Cartan criterion for semi-simple algebras, and from this follows everything. So actually the whole theory of the algebras depends on one crucial lemma in linear algebra, which I am going to show to you next time. You will appreciate this. Thank you.